Okay, thank you, Raphael. Thanks, everyone. It's a pleasure to be back in Princeton. It's been quite a while since I've been here. The title, I think, will make it clear this is a little bit more of an algebraic geometry talk than a number theory talk, but the underlying problem is quite number theoretical inspired, what's going on here. So let me explain that first. So the general context, I start with the field, and then I form the field of rational functions over that. So this is ratios of polynomials with coefficients in little k. K will be finite for a little while, and then it'll be C for the rest of the talk. And I take an elliptic curve E over K. And I'm interested in the question of considering field extensions, so L over K, a finite extension. And I'm also want to make that field itself a rational function field. So it's the rational functions in a new variable t. So for example, a standard thing that I like to consider is taking roots of the variable t. You get a tower of extensions like that, each one of which is abstractly isomorphic to the field that you started with. And then the question I want to ask is, what does the Mordell-Weil group look like as we vary over extensions like that? Okay, so I have some work in this area when k is finite. So if k is a finite field, say Fq, and let's assume that the J invariant of the elliptic curve is not an element of K. So we have an honestly varying elliptic curve. The coefficients actually involve T. And in this case, so it's always the case that there exist extensions L over K, which are rational, such that the rank of E over L is as large as you like. So I have to explain a little bit more what I mean by the rank there. There's sort of several things that you could ask for, and they're all true, but in less and less general situations. So here, rank, if you want this literally to be true, then you could look at the analytic rank. So you can ask for the order of vanishing at s equals 1 of the L function. So this is terrible notation, I'm aware. Sorry about that. So you can ask for this to be very large. So this always happens. You could ask for the Burton-Swinnerton-Dyer conjecture to be true, and therefore for the rank of the group of rational points to be large. And this is, I'll just say often, this is a little bit vague, but there's a large class of examples where you start with this and you also check the Burton-Swinnerton-Dyer conjecture, and then you know that you have a large rank Mordell-Weil group. And then in an even smaller but still significant set of situations, you can arrange for explicit points. So not just knowing that this group is large, but you can actually make constructions where you have explicit points demonstrating, or let's say filling out a large rank subgroup, generating. So depending on your desire for explicitness, you could take your pick from this list. But they're all available in at least a significant quantity of examples. What are extensions here? So under just a mild parity hypothesis, you can take L to be this sequence of extensions, say t to the 1 over n, where n varying. This works. In other words, under a parity condition on the original E over this field, as you pass up this tower of fields, you get an unbounded ranks in this analytic sense, and then in the other senses in certain special situations. And in general, what happens is that you can make a finite extension of K, again rational, and then extract roots of the parameter and put yourself in the situation where this parity hypothesis holds. Okay, so this is all kind of old, maybe the last 10 years or so, and I wanted to understand to what extent this might generalize. So what are the ingredients here in proving theorems like this? One is just the fact that we can iterate. So the fact that the rational function field can be presented as an extension of itself. in a non-trivial way. So for example, here, abstractly, this is the same as the base field, but it's a non-trivial extension of itself. We certainly can't do that over a number field. We can't present Q as a non-trivial extension of itself in any interesting way. So that's one of the key ingredients here, because this allows for some iteration. And then the other thing is, of course, Frobenius. In these explicit constructions, typically in the background somewhere, there's some kind of a Frobenius or graph of Frobenius that gives rise to geometry that gives you interesting points. So the question that I want to ask is, what happens over C? Yeah, yeah. Even in characteristic 2, 3, whatever you like. Yeah. So, of course, over C, we don't have Frobenius anymore, but we do have this possibility of iterating. And just a few years ago, I think people made a lot of optimistic statements about how if you wanted to prove high ranks over Q, you should find an elliptic curve of high rank over Q of T, and then you could specialize and get infinitely many examples. So that's very optimistic. If you hope to do something over Q of T, you should certainly be able to do something over C of T first and much more easily. So but I don't think that's very likely, as I'll explain now. OK, so from now on, K is C. And I'll write my elliptic curve in the standard way as y squared is x cubed plus ax plus b, a and b polynomials in T. And I'm going to assume that they have minimal degree, which just means that if there's some place where a vanishes to order 4 and b vanishes to order 6, you can change coordinates and scale that out. So. And then I'll define a d, which I'll call the height of E. And this is minimal positive integer such that the degree of A is less than 4d, and the degree of B is less than or equal to 6d. OK, so that'll be the setup for the rest of the talk. And I'm always going to assume that d is at least 3. I'll explain why in a minute. So the theorem is that if E elliptic curve over K, which is C of T, of height D, which is at least 3, and very general, which I'll explain a little bit later what I mean by that. And if L over K is finite, and L is itself isomorphic to the rational function field over C, then in fact you don't have high ranks. You have a trivial Morel-Veil group. So E of L is actually just 0. OK, so if you start with a general elliptic curve, there's absolutely no hope of making points on it by passing to rational function field extensions, no matter how complicated or clever you are in choosing those. So I will. The main point of the talk is to explain a heuristic that tells you why this is true. I'll also give a little sketch of a proof which isn't terribly satisfying. The heuristic suggests much more than what's in the theorem here. In particular, it tells you what to do about that annoying very general. And then I'll make a conjecture at the end about that says that the heuristic is a reasonable thing to believe, and it's very closely connected with Lang's conjecture about rational curves on surfaces of general type. OK, so let me translate the theorem just a little bit into a more algebraic geometry problem. So my E over a function field corresponds to an elliptic surface over P1. This is the guy whose generic fiber is that elliptic curve. So this is a nice smooth projective surface equipped with a morphism to P1, whose generic fiber is that. And the rational points here, so a rational point here corresponds to a section. So I have this fibration over P1. And to give a rational point is the same thing as to give a section here. This is the guy, if you take the generic fiber of that is this point. And then if you have points over, say, algebraic points, these correspond to what I would call multi-sections. So these are curves C inside E, mapping down to P1, where the degree of this, the composed map down to P1 is finite. And that's the degree of the extension L. And then algebraic points where L is the rational function field correspond to rational multisections. So multisections where this is a rational curve. So when I say rational, I mean a curve whose normalization is P1. I'm not assuming that this guy is smooth or anything like that. It's just an irreducible curve whose normalization is P1. Okay, so using this dictionary, we can reformulate the theorem. Maybe I should just say one tiny bit more about this dictionary here. So if you have an algebraic point, you get a picture like this. I think that's pretty clear. Conversely, if you have a picture like that, so a C mapping to P1 and a map here, then you can make the fiber product, clean that up a little bit, and then you sort of tautologically have a section there. Yeah? So this is why there's a correspondence between the curves inside, multisections inside E, and points over algebraic extensions. Okay, so the variant of the theorem then is that if E over P1 is an elliptic surface, of height d at least 3, very general, then E has no rational curves except the zero section, which is sort of built into our hypothesis here, and components of bad fibers. So there will be, in general, 12D places where the curve degenerates into some nodal thing or some chain of nodal things, and those will certainly be rational curves. But that should be it for a very general E. Okay, so this is the sort of algebraic geometry reformulation of the theorem. This is the thing that I want to explain a little heuristic about in just a second. Let me say a word about D in the situation on this side of the dictionary. So D in the character of the elliptic surface. So if D is equal to 0 means that your polynomials A and B don't involve T. They're just from the finite field or from the ground field, whatever it is. So that translates into the surface being the product of P1 and an elliptic curve over little k. When D is 1, then it turns out that E is a rational surface. When D is 2, E is a K3. And when D is at least 3, then you have a sort of properly elliptic surface. So the Kodaira dimension is equal to 1. And it's this last case that I really want to say something about. In particular, this theorem as stated here is certainly false in these two cases. In this case, it's sort of trivially false. In this case, it's false by some interesting theorems about K3s and rational curves. Okay, so I'd like to explain a heuristic which I think is more interesting really than the theorem, and it leads us to suspect some other things. So it's known by work of Cox that for a general E of height d at least 3, that the Picard group of E is rank 2. It's generated by the zero section in a fiber. The theorem actually will reprove this in an independent way, but let's just put ourselves in a situation where we have a surface like this. And again, sorry about the notation here. So the zero section, maybe this should be sort of a scripto or something. Squared is minus d. That's another interpretation of d. And of course, O dot f is 1, and f squared is equal to 0. So that describes the Picard lattice here. So let's take a curve. An irreducible curve C inside E and think a little bit about what can happen here. And I want to assume that C is not the zero section and C not contained in a fiber. Okay, so in this context, that guarantees that it's actually a multisection of degree bigger than 1. Now let's think about this curve a little bit. So we can certainly write it here. So the class of C in this group is a multiple of 0 and a multiple plus a multiple of f. And there are some conditions on these numbers. So C is not the zero section, so C dot O is non-negative. And if you just use the formulas here, that implies that f is at least d times E. And C, a multisection, implies that E here is at least 2. And we are assuming that D is at least 3, just to put ourselves in this situation. OK, so using these inequalities, you can go and calculate some stuff about this curve. So in particular, you can compute the Euler characteristic, well, H0 of O of C, so this is OE of C, is equal to the Euler characteristic OE of C. So this is something you can calculate. I'm not going to tell you what it is. It doesn't really matter. Some polynomial in D, E, and F. And you can calculate that the general member of the linear series C, so the set of curves which are linearly equivalent to C, smooth of genus, again, some number that you can calculate, the arithmetic genus. This is some other polynomial, D, E, and F. And then you look at the difference between those things, which is an interesting number to consider here. Okay, so when you make these calculations, it turns out that this number, I'm going to call it rho, which is essentially the difference of these guys. So I want the dimension of the linear series. That's that H0 minus 1. So the dimension of this linear series minus the arithmetic genus here turns out to be minus E minus 2 times E minus 1. Okay? And exactly in our situation, this is a negative number, strictly negative number. Okay, so far this is all precise. There's no heuristic. And now the heuristic comes, which is that I say that this is the expected dimension of the set of rational curves in the linear series C. Right? The general element is a smooth curve of this genus, and then you expect to acquire a node in codimension 1, 2 nodes in codimension 2. You expect to drop in geometric genus of 1 in each codimension. And so because this number is negative, you run out of dimension before you ever hit a rational curve. Okay, so this is some kind of a Brill-Noether theory type calculation. So that this is negative suggests generically, in other words, for E generic, there should be no rational curves in this linear series C. And we started with basically an arbitrary thing that wasn't contained in the fiber, so that leads us to expect that in fact there are no rational curves at all on a general E. Okay, so that unfortunately I don't think there's any way to turn this into a proof of anything. It is quite heuristic because of this statement about expectations. I don't think there's any strong Brill-Noether type calculations in this part of algebraic geometry. Okay, so I want to sketch a proof of the theorem, which is weaker than what's suggested by the heuristic. It only applies for a very general E, which I'll explain what that means here in just a second, and then come back to the heuristic at the end and say some other things that I think it might predict. No? No, not exactly. The proof is completely independent of the heuristic and proceeds in a somewhat different manner. You'll see. But there's a very interesting character that appears in this proof that doesn't come from this heuristic. Okay, so I want to sort of set up for a sketch of the proof, implicitly assuming that there's a zero section of height d. And this is actually a pretty concrete space. So let's write our equation down here again. So we have y squared is x cubed plus ax plus b. So I have two polynomials here, a and b. Degree generically will be 4d and 6d. So that's 10d plus 2 coefficients. And of course, I want sort of the delta function not to be 0 delta some polynomial in A and B, so I actually get an elliptic curve, and I might want some other conditions here. And then I can divide here. What's the ambiguity? What's the extra information of this choice? I can change coordinates on the base P1. So there's a PGL 2 over C here. And then there's also a C star, which is just scaling the differential for the curve. So it turns out, actually, that when D is 3 or more, that you can, this is really a slash and not a double slash. This quotient exists as a quasi-projective variety and represents this coarse moduli problem. Or it's a coarse moduli space for that problem. So this is work of Miranda's, I think, in the 80s. So this guy is so MD is quasi-projective of dimension 10D minus 2. I'm going to just call that number n from now on. Okay, and you can build a sort of universal elliptic fibration over that. So this maps over MD cross P1. Here at some point here, this is the elliptic fibration that point stands for. And we're trying to prove something about rational curves, so we can set up a Hilbert scheme. So we can construct Hilbert scheme of maps from P1 to E. So that's something that will live over MD. Call it H. And so H cross P1 will map into this X. I have a picture like this where at a point here there's an elliptic surface and a copy of P1 and a map in here where the image I here. So for each, say, X in MD, the fiber is a rational multisection on the corresponding E. Okay, now there's some general construction of these Hilbert schemes, and we know essentially nothing about this guy. On the face of it could be empty, or we don't know anything about it except that it has countably many components. And the theorem basically is that none of those components dominate MD. This guy has countably many components. Each one maps to MD, and if one of them dominates, then the theorem is wrong. If none of them do dominate, then there's a countable union of closed subvarieties of MD that contains the image of HD. I throw that away, and that's the meaning of very general. Okay, so let me just write a little bit of that down. No idea whatsoever. So, for example, in the category of my ignorance, I, for example, can't produce 1 over Q bar. I can't produce any. I'll tell you whether or not there is 1 over Q bar at this point, anyway. So the theorem prime is the same thing as saying that no component of this Hilbert scheme dominates MD. Okay, because if this is correct, then the image, the map from H to MD, lies in a countable union proper closed subvarieties. Okay, and so we remove these and call what's left very general. Okay, so this is very not explicit, as Dick is suggesting. I really don't have very much of an idea what this looks like. Okay, so the proof is going to proceed by assuming that the theorem is false, assuming that there is, in fact, a component of this guy that dominates, and inquiring into the geometry of that situation and eventually arriving at a contradiction. It will turn out, in suitable sense, that if the theorem were false, there would sort of be one Platonic universal rational curve somewhere which would induce all the other ones in every one of these elliptic surfaces. So let me explain a little bit about that. So we're going to assume that the theorem is false. Okay, and then after a little bit of work, so after some cleanup, you arrive at a picture like this. So I'm going to have a base scheme here. This is going to be of dimension n, which is 10d minus 2, but it's going to be a sub-thing of this set of pairs of polynomials. It's convenient to sort of get rid of the group action. So the space of polynomials maps down to the moduli space of elliptic circles. I'm going to take some section, linear section of that, throw away some things, arrive at an open set in there that parameterizes a nice collection of elliptic surfaces. So there'll be an x over that, which is the universal elliptic surface. And then here we'll have B cross P1 and a map here I. So for B in B, from B cross P1 to E, which is XB, is a multisection. And I also want that the moduli map here, B down to MD, is atal and dominant. Okay, so for the experts, the reason to take this atalness is that we're going to make some calculations with the deformation theory on the moduli space, and I can just lift those up to this linear section. I have very concrete calculations with polynomials. If I want to deform E, that means deforming the polynomials A and B in the linear space where they live. So this is something where you can make lots of very concrete calculations. Okay, so if the theorem is false, then we can arrange for a setup like that. And then I want to make some calculations here and see that there's some fairly exotic things that happen in this situation. So I'm going to construct a distribution. Call it script D on this total space here. So this is an n plus 2 variety, right? This is a capital N dimensional guy here. This is a family of surfaces. This is n plus 2 dimensional. This is n plus 1 dimensional. This is n dimensional. I'm going to start by considering an n plus 1 form, say omega on x. So suppose that I had such a thing. It wasn't 0. Then I observe that if I pull it back by this horizontal map at the top here, this is an n plus 1 form on an n plus 1 dimensional variety which has P1 as a factor. So it has to be 0, right? There are no regular forms on P1, so this has to be equal to 0 since it's an n plus 1 form on this n plus 1 dimensional guy. It's a top form on a variety that has P1 as a factor. Well, that's a differential condition. Every time I write down something like that, that's some condition on this map. And the way that I'd like to think about it is to give an n plus 1 form. So at a point where omega is not 0, so at say an x in script x where omega of x is not 0, you get a line in the tangent space to x at x. So you choose a top degree form in the neighborhood of that point, and then you think of your n plus 1 form as a function on one form. So you wedge and compare with the reference guy. So it's a function on one form. So it's a tangent vector. It's only defined up to a scalar because of the choice. So I get a line in the tangent space at that point. And the vanishing here is exactly saying that the image of this map, the image of the tangent space on this map, contains that line. So every time I write down an n plus 1 form, I've sort of put a differential restriction on this. I write down as many as I can, and I get some distribution. Okay, so using some deformation theory, which is very well understood in this situation by some work from the 80s, deformation theory of e's, which is quite concrete because you're just deforming these polynomials a and b, we construct enough n plus 1 forms to build a distribution. This is just the thing that's spanned inside the tangent space by all those lines I was talking about, D. So this lives inside the tangent space to x, and it has rank n. Okay, and it maps onto the tangent space to the base. Okay. So this kind of construction is something that people who want to avoid rational curves on general varieties do. And typically, say if you have a hypersurface of large enough degree in some projective space, a very general one of those guys, it doesn't contain rational curves. There's a sort of global generalization result that goes into that. You do a trick like this, and you construct something which in this case would span the whole tangent space. Here we're in codimension 2. That's not an accident. It's because we always have two classes of rational curves. We have the zero section, and we have a component of a fiber. And this turns out actually to be orthogonal to the classes of those guys in the right place. So the fact that this is codimension 2 is a good thing. That's the best that you could hope for. I mean, we're not going to prove that there are no rational curves on these surfaces, because there are some. We just don't want there to be any more than that. OK. Okay, so this all is, other than the idea to do it, is a pretty, it's a pretty concrete computational thing to compute this distribution. You can actually know, and that is that this distribution has two very concrete first integrals. Okay, so in other words, there are functions whose level sets contain tangent spaces. Level sets contain this guy. So D has two quite explicit first integrals. In other words, functions whose level sets are tangent to D. Okay, so these will be familiar functions to them. One of them is called J. So that's a cubed over delta. And the other one, you heard it here first. It's called K, and it's this guy. So it's another weight zero automorphic form up on the total space rather than on the line that parameterizes the family of elliptic curves. So it turns out after the fact that these two functions give an alternative characterization of this distribution. I mean, you just take the level sets of the pair J, K, and then the tangent space to that is what this distribution is that we cooked up in some completely different way. So to say it's a little bit of a but this is going to lead us to trouble, this little miracle. This is where the contradiction has its genesis. So we'll just consider a diagram now. I want to think about, I want to think about my rational curve parameterized by this family, and its mapping to this surface x, I here. I'm going to stick something else in here in the middle in a minute, but what I'm really thinking about here is the map to J cross K, just the pair of rational functions J and K. Okay. I've told you that the distribution, which is contained in the image of the tangent space here, is also contained in the image space of the level sets of those two functions. And what that says is that the fibers of this long map here, let's call this guy phi. So the previous board tells us that the fibers of phi have dimension at least n. Okay, there's massive collapsing along the J and K things because their level sets are tangent to this guy. So that means that the image of this guy, well, this is an n+1 dimensional variety. I have a map with n-dimensional fibers, so the image in here is actually a curve. So there's now a curve in here, z, which if you think about it for a second, is a rational curve. It's the image of point cross P1 for any point in here. So there's a single rational curve with the property that when I take its inverse image up here, it has a component which is rational. Okay, now we're asking for way too much. Right, so let's just write this down. So z here, this guy is phi of B cross P1. So z is rational. So I'll write it over here. I'm going to add a little bit more to the diagram, but all right. So z is a rational curve. That if I take, I need another map here, unfortunately. So let's have a map, which will be C. So if I take C inverse of Z and then intersect it with one of these fibers, so XB at some point, well, this has to have a component, namely the image of this P1 here. So it has to have a rational component. Okay, and I claim that this is ridiculous. If we think about how this family, essentially what's happened, we have a large varying family of elliptic surfaces, which will, by filling in the diagram here, present as branched covers of something fixed with a very strongly branched locus. And we're suggesting that there might be one curve such that it's reducible under every inverse image, which is, that's calling for way too much tangency. So what you can do in here is put the Hirzebruch surface FD, the ruled surface FD. So this maps to P1 cross, so that guy cross B, P1 cross B down to B. So this is a 2-to-1 cover. This is a guy whose coordinates are x and t. If the coordinates of your original elliptic surface were x, y, and t, this is just x and t. So this is a double cover branched over the polynomial x cubed plus ax plus b equals 0. And then there's a map here and a P1j here. So here I have a point B, which is essentially a pair of polynomials a and b. And if I have an a and a b and a number t, then I get a j invariant. So this is j and this is j cross k. The k function was x times a over b, right? It only involves x, not y. So it factors through the surface here. So this guy, so x to f d, now let me write this over here. Okay, so the family x mapping to this ruled surface cross B is 2-to-1 cover branched over the set where x cubed plus ax plus b is equal to 0. A and b are varying. They're essentially varying through a maximal dimensional linear space inside. That's the base space here. And then the map from FD cross B to P1J cross P1K has degree 12D. It's essentially the J map in the second coordinate, and its branch locus varies over an open set in now it's essentially P1. It's not J, it's P1T, excuse me, this guy to some large number, which I forget now. I think it is 10D minus 4, something like that. So whatever the Riemann-Hurwitz formula tells you for the number of branch points for a generic degree 12D map from P1 to P1, and this is saying that the branch points there vary through a big open set of the relevant space. So then it becomes a very classical argument, right? It's easy to check that, in fact, with strongly varying branching data, as in these two situations, if you take a rational curve here, which of course we don't know anything at all or very little about because it doesn't in fact exist, but anyway, any rational curve with just a tiny bit of information and strongly varying branch data like that will have the property that its inverse image in here is irreducible of large geometric genus, and so that leads to a contradiction. We didn't actually really have the family that's here. Okay, but as has been pointed out, this is really non-explicit and not completely satisfactory in terms of being able to point at something and saying something about race.
Would you prove over? Let's see if I over Q bar. Is it true that you proved that no component of the Hilbert scheme covers the module?
No, because I had to throw away a countable collection of things, so I might have thrown away all of the Q bar points of a moduli space. Yeah, I don't. There's nothing left over Q bar in this argument, unfortunately.
I see. So C is not. You're not.
It's that it's uncountable.
Incidental about C, just that it's uncountable.
That it's uncountable, and in fact, so the theorem, in some sense, is false in characteristic P because we have these examples, but there are only countably many of those examples. And I think this theorem was actually true over an uncountable P. Despite the different, there's some. I actually think it works in that situation. Uncountability that's playing a role here. No.
All this is completely algebraic.
Yeah. All the calculations, the differential calculus, all that stuff was just algebra. Yeah. Okay, so that's unfortunately what I know how to prove here. But I would like to speculate a little bit by going back to the Brill-Noether number and think about what that might be telling us. All right, so we'll come back to the heuristics. Okay, so we had this number rho, which was the expected dimension in this linear series C. So it was the dimension of this guy minus the arithmetic genus, typical member here. So this was minus d minus 2 times e minus 1. It was a negative number. So sometimes in Brillouin theory, when there's a negative number, it tells you that that phenomenon doesn't happen generically, but it should happen in that codimension of the absolute value of that negative number. So one might speculate. So one can, let's just say it that way. So one might speculate that the absolute value of rho is the codimension of the locus where we do see rational curves. It takes a minute to think about that. That is a meaningful statement because it's not really a C here, it's really a class in this PIC involving O and F. That exists over the whole moduli space, so I can look in that linear series in every E and then ask how often does it happen that there are more degenerations than would be expected. Okay, so the number on the right-hand side involves D and E. On the other hand, the dimension of this moduli space does not involve E. It was this number n. It's 10d minus 2. Okay, so in particular, if E is big, this would suggest that, in fact, there aren't any rational curves. Now, if E is sufficiently large, then we might still expect no rational curves in this linear series C. Well, what was E, right? C was equivalent to E times O plus F times F. So E is simply the degree of the map from C down to P1. Say it's the degree of the multisection. So the speculation here is that there are no rational multisections of very large degree over the base, and you shouldn't take the numbers here at all seriously, as suggested by this, because I made the simplifying assumption that I had a PIC with Z2. The PIC could be much more complicated, and the numerics are more complicated in general. I don't stand by the numbers that are thrown out by this. I'm just putting this forward as a suggestion for expected behavior. Okay, so that's a conjecture we can make, which I am willing to make. Okay, so the conjecture is that no rational multisections of large enough degree over the base P1. Okay, this admits a very nice reformulation, which makes it fit in with other stuff and makes it a little bit more plausible. Wouldn't be willing to conjecture just based on this heuristic, but the other things that it fits with very nicely give it a little bit more plausibility. So let's reformulate this. So we note that the canonical bundle of an elliptic surface of the type we're talking about is d minus 2 times the fiber. This conjecture says it's equivalent to the statement that if you consider the collection of integers C intersection product with the canonical bundle, where C here runs through rational curves inside E, so that this set of integers is bounded above. Okay, just a reformulation based on this observation. But this conjecture exists as a conjecture in certain contexts as a theorem in other parts of the world's surfaces. So let's note that if S is a surface with codiary dimension of S less than or equal to 0, then the set of things like this, Ks, C inside S rational, this is trivially bounded above because, well, if the quadratic dimension, if K is trivial, all these numbers are 0, and if K is sort of anti-ample, then they're certainly bounded above. And if S is of general type, then this set of numbers, C dot Ks, or C and S rational, that this is bounded above. Is equivalent to Lang's conjecture. So which one of Lang's conjectures? So Lang conjectures, among other things, that a surface of general type should have only finitely many rational curves on it. Certainly if it has finitely many rational curves, then this number is bounded above. But those rational curves don't move in their linear series. So if you bound their degrees, you actually bound them in numbers. So Lang's conjecture is equivalent to that statement. So you can package all this together into one very clean conjecture, which I'm willing to make, and that is that that statement is correct for any surface. So if S is a smooth projective surface over C, then the set of integers C dot Ks, where C and S is rational, is bounded above. Okay, now I have no idea how to prove that, but I think it's quite nice that this heuristic, what the heuristic suggests for elliptic surfaces, fits perfectly with Lang's conjecture for surfaces of general type, and the corresponding statement is trivially true for the other kinds of surfaces. Okay, and let me finally come back to the original question about ranks and just state as a little proposition. It's quite easy to prove, and that is that if this conjecture is true, and E over C of t is an elliptic curve with the J invariant of E not contained in C, then the set of integers rank E of L, where L over K is finite and L a rational function field, this guy is bounded. Okay, so starting with elliptic curve, non-isotrivial elliptic curve over a function field, you may be able to increase the rank some, but the totality of ranks over all possible extensions of this type should be bounded. Okay, so that's all I had to say. Thank you very much.